Gaat u alle zitten. Dear colleagues, Professor de Vries, dear family, friends of Professor Bert de Vries, ladies and gentlemen, good afternoon and a warm welcome in the auditorium of our Eindhoven University of Technology. My name is Ton Baks. I'm Dean of the Faculty of Electrical Engineering. I'm Vice Rector of this university. And we are gathered here on the occasion of the inaugural lecture of Professor Bert de Vries, entitled In Situ Personalization of Signal Processing Systems. It's my great pleasure to say a few words of introduction to the lecture that Professor de Vries will give in a moment. As we all know, our society is faced by a number of major challenges, such as the energy problem that we have, mobility, health problem, and all these areas are strategic areas of our university. Innovative technological concepts are needed to tackle these challenges, and we as a university consider it our duty to make a significant contribution to achieving this. By producing top quality engineering graduates and by devising and developing technological concepts that can be utilized throughout our research and valorization. This is why we have professors like Bert de Vries, people of the very highest level. In a few minutes, Bert will tell us more about main trends in the field of hearing aids technology. And what we can say there is, and Bert will definitely say more about it, is that despite a decade of steady industrial and academic investment in signal processing technology for hearing aids, about 20% of patients remain unhappy with the sound quality of their instruments, of their devices. And as it turns out, we can design a fine hearing aid for a given person in any given situation, but we don't have enough upfront information to design a great solution for unknown clients who live in a volatile acoustic world. Therefore, Bert states that hearing aids must be both adaptable to the environmental context and personalizable by the patient who is making use of these devices. In his lecture, Bert will address the design challenges and the opportunities of adaptable hearing aids, and more generally of signal processing systems which can be personalized in situ by end users. He will also tell us more about a few salient properties of a successful, adaptive and personalized signal processing system, namely our brain. Before giving floor to Bert, I would like to say a few words about his career up to now. In 1986, Bert got his Master of Science degree in electrical engineering from our university, actually from our department. And in 1991, he got his PhD in electrical engineering from the University of Florida, USA. Between 1992 and 1999, he was a researcher at the Sarnoff Research Center in Princeton, New Jersey, USA, where he conducted research on a wide range of signal and image processing topics, such as speech recognition, financial market prediction, and breast cancer detection, to mention a few. Since 1999, Bert has been back in the Netherlands, working in the hearing aids industry, first with Philips Hearing Systems, and then, following some company mergers, with Danish hearing aid manufacturer GN Resound, both in scientific and research management roles. Also since 2004, Bert has been affiliated with the Signal Processing Systems Group at our university, chaired by Professor Jan Bergmans, as a research fellow between 2004 and 2011. On April 1st, and this is not a joke, last year Bert was appointed part-time professor of personalization of medical signal processing systems in the Department of Electrical Engineering at our university. Bert is a top scientist who has a clear and a powerful vision of cooperation between universities and industries, as well as the way in which more intensive use can be made of users in improving hearing aids and their capabilities. He also has good connections with the Signal Processing Systems Group and many links with other departments and companies. Bert's CV is broad and his list of publications is impressive. He has authored and co-authored about 60 scientific publications and 13 patents. In short then, his knowledge, experience and network make Professor de Vries an important bridge between the department's research and the field of application. Professor de Vries, we are very happy to have you on board and we wish you a successful career at our university. Before I give floor to Professor de Vries to speak out his lecture, I would like to say, to mention a couple of things, logistic things to you. After the lecture, there will be a reception in our Senaatzaal, and our Senaatzaal is opposite to this room, so we will leave later on through those doors. You then have opportunity to congratulate Professor de Vries and his family, but I would like to ask you to not form a long queue. It's better to get into the room, have a drink, watch how long the queue is, and when it's not too lengthy, you can get to the end and congratulate. Bert, may I invite you to step forward?
Dank u wel. Dank u wel, meneer de decaan. Dames en heren, ladies and gentlemen. It's great to see so many familiar faces. It's an honor and a pleasure for me to get the opportunity to do this inaugural speech today. I think an inaugural speech should be about the future. The word inaugural refers to a beginning. And since I work for a hearing aid company, I will talk about my ideas and my plans on how to improve hearing aids in the near future and also a little bit beyond that. Towards the end of the lecture, I would also like to extend that and would like to convince you that the ideas that I talk about have actually a wider range of applications, and I'll mention a few of those. So to start off, let's try to experience what it is to be hearing impaired. I'm going to play a video clip, and this is a clip from the Flintstones. And there's a hearing loss model built in. And as the clip moves on, you will progressively get more hearing loss, or at least this will be simulated. So let's see if that works.
1, 2, 3, 4, 5, 6, 7. You're on my apartment building on Private Avenue. You owe me $300. Get it enough?
Take it easy, it's only a game.
Well, I'm just like them big tycoons. I play to win. I've already paid up or I'll get out of the game.
So obviously, this is a problem if you suffer personally from hearing loss, but it's actually a bigger problem, or a big problem for society. 1 out of 5 Americans over the age of 12 suffers from hearing loss to a degree that impacts their communication skills. And the problem is beyond communication. People with hearing loss actually have a much higher chance for developing dementia later in life. Hearing loss is also by far the biggest bill for the Department of Veteran Administration in the United States, because it is the most prevalent disease for soldiers returning from combat. So hearing loss is quite a big problem for society. Usually the problem is it occurs in the cochlea. The cochlea is a small organ about a few centimeters behind the ear, where mechanical vibrations are transduced into electrical signals, and then these are transported up the brain. And as you grow older, or because of a loud sound, the cochlea will break down. And this is usually not repairable. So people who have a problem with the cochlea, and almost everybody of an older age will have a problem, they are a candidate for hearing aids. A hearing aid is an electroacoustic device. It has a microphone that captures the sound. Then this sound is processed by electronics, either a computer program or by hardware. And the resulting sound is sent to a loudspeaker, and then it goes to your ear. And there are many different forms and sizes of hearing aids, different colors. This is from the ReSound family of hearing aids. And each one concerns a different engineering trade-off or a different user preference. So I work for ReSound, and ReSound is one of the larger hearing aid companies. It's headquartered in Ballerup, but this is very close to Copenhagen. There's also a large facility in Glenview, which is a satellite town of Chicago. And there is a very small facility in Eindhoven. But we are with 15 people, and we are located here, 200 meters away here on the campus of this university. And we are an engineering group of 15 people, mostly working on signal processing. Now, ReSound is mostly known for its unique capacity in wireless communication. If you buy a ReSound hearing aid, you can stream sound straight from the TV into your hearing aid, or you can control your hearing aid from an iPhone with an iPhone app. And in that sense, ReSound is quite unique. Now, how do patients, do they like hearing aids? What is the patient satisfaction rates for hearing aids? So this is a graph from a marketing study, and this is industry-wide from 2010. Vertically, there are different aspects of sound processing. At the bottom, it says wind noise, and there is a category how you deal with soft sounds. And horizontally are patient ratings across a large group of patients. Green means they're very satisfied with that aspect of sound processing. Red means they're very dissatisfied, and gray refers to a neutral opinion. And you can look at this for a long time, but roughly 20% of customers are not happy with the sound processing in their hearing aid. And that is actually, I think, a remarkable number, because we in the hearing aid industry, and also together with academia, we've been working on hearing aids for more than 10 years, at least on the digital signal processing. So if I add up the amount of researchers and scientists that work on signal processing, we've invested easily more than 1,000 man-years, which means it's the equivalent of one person working 1,000 years. And still, 20% is not so satisfied. And you can speculate about why that is, but my conjecture is that it's due to the large upfront uncertainties. And by that I mean that when an engineer designs a hearing aid, he doesn't know who the patient will be. He doesn't know where he's going to walk, in what kind of acoustic environment, and he doesn't know what kind of hearing loss this patient has. And several aspects are also time varying. There is buildup of earwax in the ear. There is, every time a patient puts in a hearing aid, just a little different, and this affects the acoustic situation around the ear. So for an engineer, he cannot design the optimal hearing aid because he doesn't know what the optimal hearing aid is. And that means that it's easy to think of a solution. Well, if we know we're going to get it wrong up front for a large amount of time or a sizable fraction, we should just design hearing aids so as to make it easy to adjust hearing aids in the situation, or in situ, as it's sometimes called. So in situ redesign must be easy. And currently, it clearly is not. Now, this sounds to me a very reasonable approach, but I would like to convince you that it's a bit more than a reasonable approach. This is actually a tested engineering approach. So I'm going to tell a completely different story now, or about a different engineering problem, to show where this approach has been tested. Henry Kramer was a British industrialist in around the 1950s, And he was obsessed with human-powered flight. And so he created the Henry Kramer Prize, right? What else? And the Henry Kramer Prize was a prize for 50,000 British pounds for the first team that would fly over a route of about 1,600 meters, 1 mile, in a figure eight. And 50,000 pounds at that time is the equivalent of €1 million today. So this was a big prize. So many teams would go ahead and try to build that plane. And they would spend a year on it, engineering and on the plane and doing math and computer work. And usually they would spend about a year. And of course, the plane in the test flight, they would take off and crash. And they would basically throw away this year's worth of effort. And then came another avionics engineer, Paul MacCready. And this was 18 years later. And Paul MacCready reviewed 50 attempts, 50 failed attempts. And he looked back and he reviewed what these people did. And he said, we've been trying to solve the wrong problem. The problem was not how to design the best human-powered flight. The problem was that they did not understand the problem. So Paul MacCready set out to design in a different way. He said, let's try to build planes that can be rebuilt in hours rather than months. This is a completely different objective than the objective, let's try to build the perfect human-powered plane. And so he built planes with his team made of duct tape and plastic foil and aluminum tubing. And I actually have a little clip from one of such iterations.
Let's get up about 3 feet. Okay. 35. Stop rattling! Stop rattling! Go left! You go down.
The builders learned from both crashes and computer programs, and they made many changes to create the final airplane.
So this would go on for more than 200 iterations in early 1977. And in August 1977, just half a year after they started, they actually managed to fly the 1,600-meter route and claim the prize. And 1 year later, because they continued this approach, 1 year later they built this plane. This is the Gossamer Albatross. And with this plane, they flew across the English Channel, claiming the 100,000-pound prize, the second Kramer Prize. And so what this is, of course, a completely different engineering problem than hearing aid design. But what both problems have in common is the large amount of uncertainty about operational circumstances. So my view would be that in research, we should not really try to design the optimal hearing aid. Rather, let's try to design hearing aids that can be redesigned fast under operational circumstances to deal with the problems on the spot as they occur. And this is actually very difficult. If I compare the current situation to this challenge, it's a very large challenge. Today, when a hearing aid doesn't work or you're not satisfied under operational conditions, we don't have tools to repair that. So the hearing aid will generally go back to the engineer where he starts up his computer and he starts working on the signal processing, and a few months later he may have a new design for the signal processing. But what I'm actually after here is that if there's a problem in the field, that a patient can do a design iteration. So we replace an expert by a lay person. It should be under operational conditions on the spot because you cannot recreate the problem in the lab. And a design iteration, it should really sound better in about a minute, because if it doesn't, then the patient will not spend the time the next time. Any of these three aspects is a giant leap. So in some respects, this is a crazy goal to go for. But on the other hand, which one would you like to take away? You cannot ask the engineer to go out in the field and walk around with the patient. And so this is really the optimum solution, but it sounds very difficult. On the other hand, there is a system that does just that. For the brain, this is the bread and butter. A main function of the brain is to make models of the world, of the sensory signals that we receive, and to try to predict how the world evolves in the near future. And we need that to survive. If I step onto a road and there's a car coming, I need to predict what will happen, otherwise I may not survive. I need to be able to predict which physical situation are hostile for me or potentially poisonous. And in order to do that, I need to continuously update my model of the world. And the brain doesn't need a lab to do that. There's no engineer, and it needs to be very fast. It needs to update on the spot as the problems arise. So these three conditions that we're after are actually a specialism for the brain. And so what I will do in the next 20 minutes is compare some aspects of computation in brains to computation in hearing aids, and see and look at the contrast between where do hearing aids currently fall short in relation to what brains can do. So let's do it by an example. Let's say that I'm on a cocktail party and I can't understand my conversation partner. So now I need to do a design iteration. And a design iteration consists of three aspects. I need to change something. I need to change the signal processing, either change the parameter or change the algorithm. I need to evaluate this new alternative, if it's better or if it's worse than the previous model that I had. And if it's better, I need to do more of it in the future. And if it's worse, I need to do less of that. And that's called adaptation. And these are the three steps we need to do for an iteration. Probably the first try will not be the one that I need, so I need to iterate. I may have to do it again and again, but not too often, because nobody will want to go on for 100 times to do this. Since this has to be done in the field, and it has to be done fast, we want to automate this process, this design iteration, as much as possible. And let's see how that works. So here is the hearing aid algorithm. This is the signal processing, or a diagram of the signal processing in a hearing aid. And now I'm in the field and I'm not happy, so I want to make a change. And what can I do? Well, I can add some stuff to it. I can add some blocks, right? Or I can take something away. Now, if your experience with electronics is like the same as mine, this will probably crash. This circuit will die, right? Why will it die? Because, well, I don't understand this circuit, so I'm just doing something, and probably there will be a snowball effect of changes. I will make a change somewhere, this will affect a module somewhere else, this will have an effect somewhere else, and this will crash. So that means that this circuit is not really fit for fast redesign. I cannot easily or automate the process of trying an alternative. And why not? Even if you do not understand anything about signal processing, I think you can still recognize something about this circuit, namely that this circuit is handmade. This is not a natural circuit that could have evolved in nature. If it would have evolved in nature, there would have been a natural 50% point here that would work, that would be functional, and a natural 70 and 90% point. And this circuit just doesn't have that. And as a result, there also isn't a natural extension point or a natural point for making it simpler. In nature, every complex system is the way it is because it evolved that way. This circuit could not have evolved in a natural way, and therefore it cannot be automatically extended. So brains do that differently because brains have to try alternatives too. And brains use the concept of modularity. Modularity means that a system consists of smaller subsystems where the dependencies within a subsystem may be large, but between the subsystems, between the modules, there are very few dependencies. And that really reduces the snowball effect. If I make a change here, the chances for this change to have effects on other modules is drastically reduced if I have modularity, and therefore I can redesign. And also, if things are modular, there's a natural way to redesign, namely just copy or replicate. This is the nature's way of extending systems. If I would just have modularity, that wouldn't be enough because if I want to have behavior, functional behavior that is more complex than for the individual modules, we will need to have interactions between the modules. And that leads, but we don't want the snowball effect leading to a crash. And this leads to hierarchies. And in order to show you the virtue of a hierarchical system, I'm going to tell you the watchmaker's parable, which is a story that Herbert Simon wrote about in 1969. There are two watchmakers, Tempus and Hora, and both designed watches consisting of 1,000 parts. And sometimes they would get a call while they were busy from a customer, and they would have to answer the call, and at the end of the call, they would have to start over again. And Hora did very well with his store. But Tempus actually didn't do well. His store, he couldn't maintain his store. So what was the difference between the two? Well, Tempus would try to build these watches consisting of 1,000 parts. And if he got a call somewhere in the middle, and he would answer the call, and at the end, well, he would lose sometimes 600 steps, or sometimes 300, but on average 500 steps. However, for Hora, he would also have 1,000 parts, but he would put 10 pieces together and put a wrapper module around it, and this was stable. Then he would put together the next 10, put a wrapper module around it, and keep it stable. Until he had 10 wrappers and put them together in a super wrapper module. And this process would continue, and so he would get a hierarchy of 1,110 modules and a watch. And if Hora would get a call, after the call, he would only lose at most 9 steps, and on average just 4.5. And from that, he could recover. So modularity really facilitates building complex systems. Hierarchies facilitates building complex systems. And modularity facilitates automated model building. So hierarchical modularity is the essential structural concepts that brains use in order to be able to generate by itself automated new alternatives. Now, there's a second aspect of brains that is not commonplace in signal processing circuits. After I have managed to generate an alternative and I need to compare the two, I need to do two operations. I need to evaluate if this new alternative is better or worse, and I need to adapt. Like I said, I need to do more of this new alternative if it's better and less if it's worse. And the calculus to do that, the fundamental calculus of dealing with uncertainty and therefore for learning and adaptation is probability theory. And this is the same probability theory that we all learned in high school and tried to forget afterwards, but you're still using it. Maybe not consciously, and I'm not saying that the brain really computes everything with the rules of probability, but the way it reasons is very consistent with probability theory. And that means that brains have implement a very fundamental framework for learning and adaptation. There is a rule in probability theory called Bayes' rule, and this is the formula. And this rule is extremely fundamental for every process that relates to adaptation and learning. What this rule does is it assimilates existing knowledge with new observations. So if I have existing knowledge in a model, it says here PR, the probability distribution over a model, but that's just a model. Before I make an observation, and then I make an observation, let's say I listen to an acoustic sound, and this model could be a brain or a computer program, then Bayes' rule assimilates the observation and the model into a new model, and this is the model that has now, this is the model given the observation, given the data. So I've learned, I've absorbed the information from the observation. And how does Bayes' rule do that? Well, there are two factors here, PR data and PR data given model, and I'll discuss a little bit about these two factors next. The first factor, PR data, probability for data, is the way how brains are able to evaluate how good a model is. And what does that mean, how good a model is? Let's say I make some observations in a two-dimensional space. I have just a bunch of data points. And I try to think of a mechanism that could have produced these data points, an explanation, a model for these data points. Well, the first thing you can think of, I just have a box, and I randomly sample from that box. And that's a good model. It's simple. But I have not, there's kind of this empty bar here, and I've not explained it. So this is a simple model, a simple explanation. It's not very accurate. We can fix that. We can make the model very accurate. Now I have a whole set of models. And I sample now from each submodel one data point. This is very accurate. But actually, this model is as complex as the data point itself. For each model, I'll still have to describe what the coordinate is. So this doesn't explain, this model is very accurate, but it's too complex in a sense. Intuitively, you feel this is the explanation we would prefer. It's simple enough, and it's also accurate enough. And this is also the model that Bayes' rule chooses. Between these three models, Bayes' rule selects this one as the best explanation for the data. And it does so. What is the relevance of it is that it tries to maximize accuracy, and that's great. Accuracy means it tries to fit the data that has been observed. That's very important for today. But on the other hand, we don't know what the future will be. We may have to adapt in the future, and therefore we need also a simple model. Our brains need to be able to adapt, and so brains will choose this one because simple models are more adaptable. In a sense, by being consistent with probability theory, brains optimize both for today and also for an unknown future. And that is a fundamental characteristic of proper modeling and of brains, and actually we need that, of course, to survive. And also we need that in hearing aid design, because in hearing aid design I also need to balance between something that works now and circumstances that may change in the future, but I don't know yet how these circumstances will change. The second term I want to say something about is this term, the probability for the data given a model. This term discusses or describes an expectation. It says, what is the probability that my observation occurs given my model, given my brain? In other words, in order to do adaptation, I need to first make an expectation. I first need to describe how likely is that observation. And I can actually show that our brains do that. Because perception is an adaptive process implemented by the brain. And what you see here, this is, you probably see a bowl of vegetables, right? If I turn this bowl of vegetables upside down, you will probably first see a gardener, a face, rather than an upside bowl of vegetables. And the reason is that we've seen so many faces in our life, we have a very high expectation for seeing faces. We don't have a very high expectation for seeing upside bowls of vegetables, right? So we tend to see what we expect to see. We tend to see what is consistent with what we've seen in the past. And this is also very important when we do adaptation. This is a principle of adaptation in the brain, and it's currently not implemented in many signal processing systems. The third aspect of computation in the brain that's unusual for engineered signal processing systems is how can we do so much with so little? If a mother points out 1 or 2 trees to a 2-year-old, then the tree is able from that to generalize to all kinds of trees. The child will be able to point out trees everywhere, and will even be able to discriminate from objects that are not trees. And given the various sizes and shapes and forms and colors of trees, it would be impossible to learn that from these 2 teaching events. And indeed, a child or any person doesn't learn what trees look like from her mother. We learn what trees look like from observing the world, and we receive millions of bits of visual data every second, and we model the world, and we model a cluster that looks like trees, and when the mother says that's a tree, then we just put a label on that. In fact, the brain has about 10 to the power 14 synapses, which I consider roughly the parameters of a brain. And we live on the order of 10 to the power 9 seconds. So we have capacity to train 100,000 parameters every second in our life. And you could never learn anything close to that from interactions with teachers, with parents, or with books. Most of what we learn goes through modeling the world, and what the teacher and what the parent does is just modulate that data stream, putting a label on it, putting an attention mechanism on it. In the same way for hearing aids, if I listen to a hearing aid, here's audio, here's a hearing aid, here's the audio going out, and I'm not happy, and I decide to make a change to the structure, and I want to evaluate it, and I want to express and tell the iPhone that, oh, I like it better, or maybe I do not like it better. That's 1 bit of information. That's a very tiny amount of information. That is not enough to train the parameters in a hearing aid. In a hearing aid, we have 1 million bits of acoustic information flowing in the hearing aid every 4 seconds. And in the same way as brains learn mostly from the environment, also hearing aids should learn mostly from the environment and use interaction with a patient to modulate those data streams or to put labels on those data streams. So to summarize what I just talked about, I talked about the fact that in the design of hearing aids, the biggest problem is that we have uncertainty about in situ circumstances. And I think an engineering solution is to build systems where we can iteratively, fast iterate through design iterations in the field. Currently, we cannot do that with our signal processing. But brains can do it. And why? What are some of the computational principles of why brains can do it? Well, brains have a different structure that allow automated model building and also build complexity. Brains have a very proper framework for assimilating, for putting together new observations with existing knowledge. This is probability theory. It's difficult to actually realize probability in circuitry and in computer programs, but brains manage to do so. And in current industrial hearing aids and in many signal processing systems, we are not able to do this yet. But brains are able to adapt correctly, and also brains learn mostly from the environment. And that, as a result of that, we do not need as many iterations as when we only learn from interaction with teachers, with parents, with patients. So these are the ideas that are not yet implemented in hearing aids at the moment. And so my research in the future will be how can I implement some of these ideas in hearing aid signal processing. And I want to carry that out at the university with students in collaboration with my company. Now I'm going to extend the conversation a bit to some other applications. Engineers are very good. Engineers have a large toolbox of methods to solve problems. We tend to look at a problem, analyze the problem, and choose the tool, choose the appropriate tool for any problem. Brains do not have that luxury. Brains are very good at data modeling and try to solve problems by data modeling. I've just discussed a bit why brains are so good at data modeling. We try as much as possible every problem that we encounter to solve it as a data modeling problem. Data modeling is cheap, it's mostly unconscious, and almost 99% of our processing is unconscious. But brains do not know what problem will be thrown at the brain, right? If I look at the cortex, whether it's the auditory cortex or the visual or the motor cortex, structurally it's all the same. There is one big, very powerful algorithm for modeling. So brains have a big hammer, a big solution for many problems, rather than a different solution for every problem. So the expectation, my expectation would be that if we start designing signal processing more like brains, more neurally inspired, that we might actually get signal processing systems that are have a much broader applicability. And I think if I look at projects that are going on, for instance, in our signal processing group at the moment at the university, like patient monitoring, where the problem is how to infer the status of a patient or a fetus from observations with sensors, or smart homes, how to control temperature and humidity so as to maximize comfort for the inhabitants and at the same time minimize energy consumption. Or intelligent lighting, how do you please people in the room automatically by changing lighting conditions? If we would know exactly the environment and we would know exactly the preferences of users, then we could design such controllers and these signal processing systems. And why it's difficult is because patients move, patients sweat, somebody will open the window, somebody will move the furniture, things will change in unforeseen ways. And in a sense, all these problems are difficult, just like the hearing aid problem, because of the unforeseen circumstances that make it difficult. And this is a trend that will increase, or the importance of finding solutions for these types of problems will increase. There is, particularly through the internet, an enormous amount of information and data available at the moment. I read that every minute, more than 600,000 gigabytes of data is sent around the internet. And more than 1,300 new smartphones are connected for the first time to the internet. So there is a tremendous amount of information that can be streamed over the internet. And so there is a tremendous amount of problems that can be analyzed automatically and probably solved. But there are two important aspects. One is there are so many problems and we don't have enough engineers to solve these problems. So we need automated model building. The second is that data is most valuable at the moment when it's created. If I want to predict whether some piece of machinery will fail in the future based on analysis of acoustic emissions from this machinery, I need to have the most recent data. I cannot store it in a database, wait 3 months, and then look at it. So we need online learning, continuous updating, and we need automated model building. And so there is currently a trend going on of companies who jump in this hole. And I'm just mentioning this as an example. Numenta is a company founded by Jeff Hawkins. Jeff Hawkins was formerly the founder of Palm Pilot and now created a company, Numenta, that has a product called Grok. And Grok is a model that is built automatically. You can stream data from measurements over the internet to Grok, and it doesn't matter. It could be trading signals, it could be acoustic signals or signals from any kind of sensors. Grok will build a model automatically, and it will try to predict the future of your data or detect unusual events. And Grok is completely automated. Grok is completely neurally inspired and uses some of these principles that I talked about: massive online learning, high degree of hierarchical modularity, and Bayesian or probability theory for its adaptation. In a sense, all these problems, patient monitoring, hearing aids, Grok and future Groks, are related by the fact that they all are concerned about how to deal with unforeseen future circumstances. And so I believe that progress in signal processing for hearing aids and progress in signal processing for intelligent homes are also therefore related to how much we will be able to learn about our own human information processing. Then this concludes the technical part of my presentation. And I would just like to go over now to thank a few people that have helped me along the way. And this includes friends and family and colleagues. And so at the university, I would like to thank the dean, Ton Bax, for enabling this position for me, for encouraging support and interest whenever we have a conversation about my work. I would like to thank Professor Jan Beneken, who's in the room, who gave me a chance in 1985 when I graduated from this university under his supervision. He let me do my thesis work in Florida. This was a great experience. I stayed for a long time in Florida, had a big impact on my life. I'd like to thank you for that. Charlie Chalkins, who is here. I teach a class together with Charlie, and that's a lot of fun and very rewarding. I'd like to thank all the students from the signal processing group. This is the signal processing group. Students that I work with, it's really fun for me to work in your projects with you. And most of all, I'd like to thank Jan Bergmans, who is the chair of signal processing. And Jan has really been the main driver behind this appointment and is a great mentor for me. And in a way, I would feel a bit too self-centered to just consider what Jan is doing for me, because Jan is the chair of this signal processing group, which is really a powerhouse in academia. There are 5 IEEE fellows, 8 startup companies over the last decade, consistently top-ranked group. And it is really a pleasure to work in this group, and it's really due to, or for a large part, to Jan Bergmans. And the only problem with Jan is that he's so much about helping others to succeed and putting others in the spotlight that this is the best picture I could find for Jan. Then at Resound, I work at Resound. It's a great company to work for. Resound is really committed to technology, to the advancement of technology for hearing impaired people. And so I feel really at home there. I'd like to thank the senior management of Resound for giving me this opportunity, in particular the VP of Research, Andrew Ditburner, for support and encouragement. My colleagues in Chicago, in Copenhagen, and in Eindhoven. And this is the Eindhoven group. We like to dress up for the occasion. It's a great group to work with. They provide a really great environment, both professionally and team spirit, and I'd like to thank every one of them. To mention or to single out a few names would detract from the others. I'll just mention Jos Lene here, who was there already when I started. He's been a great friend and team leader for us. This is after work, but you see, sometimes we have a beer after work, but we always have work with us. So I'd like to thank the Eindhoven group for the great environment. And finally, of course, I'd like to thank my family, my parents. I think we should follow my father's lead here and have a drink. I've been supported in many ways by my family, in all the good ways. I have great sisters and a great wife. En mijn dank jullie is groter dan ik hier kan uitdrukken. Thank you.